A galaxy is a gravitationally bound system made up of stars, stellar remnants, interstellar gas, interstellar dust, and dark matter. What makes a galaxy feel calm when studied is not just its size, but the way that size is expressed through extreme slowness. Typical galaxies contain anywhere from tens of millions to hundreds of billions of stars, yet those stars are separated by enormous distances. Even in relatively dense regions, the average distance between stars is measured in light years, not kilometers. This means that most of a galaxy's volume is empty space, creating an environment dominated by quiet separation rather than crowding or collision. The scale of a galaxy is difficult to intuit because it does not behave like large objects on Earth. A spiral galaxy similar to the Milky Way is roughly 100,000 light-years across. Light itself, the fastest known signal in the universe, takes 100,000 years to travel from one edge to the other. Within that span, individual stars move slowly in wide orbits, governed by gravity that acts steadily rather than forcefully. Nothing in a galaxy moves quickly by human standards. Speeds that seem large in numbers translate into motions that take millions of years to become noticeable. Galaxies are not solid objects. They do not have edges in the way planets do. Instead, their boundaries fade gradually as star density decreases. This creates a natural softness to their structure. There is no sudden transition from inside to outside. Stars become fewer, gas thins, and eventually the galaxy blends into intergalactic space. This gradual change contributes to the sense of continuity rather than abruptness. The mass of a galaxy is spread across vast distances. Although gravity binds everything together, that force weakens smoothly with distance and balances with orbital motion. Stars are not pulled violently toward the center. Instead, they follow stable paths that repeat over and over. Many stars complete only a few dozen orbits over their entire lifetimes. Each orbit can take hundreds of millions of years. This repetitive, predictable motion creates long-term stability rather than chaos. From a physical perspective, the interior of a galaxy is extremely quiet. Space does not carry sound the way air does, so stellar explosions, stellar winds, and motion occur without noise. Energy is transferred through radiation and gravity, not vibration. Even dramatic events such as supernovae unfold over days or weeks locally, but are isolated by immense distances. Their effects fade long before reaching most other stars. Galactic scale also smooths out extremes. Temperature differences exist, but because space is so sparse, heat transfer is inefficient. Regions can remain cold or warm for very long periods without sudden change. Gas clouds may drift for millions of years before forming stars. Nothing is rushed. Processes begin, continue, and conclude slowly, governed by physical laws that favor gradual evolution. Another calming aspect of galactic size is statistical balance. With billions of stars, individual variations average out. While one star may be forming, another may be aging, and another may be ending its life, the galaxy as a whole remains steady. Its overall appearance does not change dramatically over human timescales. The same patterns persist for thousands of generations. Dark matter plays a significant role in maintaining this stability. Although invisible, it forms a massive halo around galaxies, contributing most of their gravitational mass. This halo keeps stars in orderly orbits and prevents the galaxy from dispersing. Dark matter does not interact violently. It influences motion silently through gravity alone, reinforcing long-term calm rather than disruption. When observed from afar, a galaxy appears as a soft concentration of light. This glow is not intense brightness, but the combined output of countless stars diluted across distance. The light arriving at Earth has often traveled for millions or billions of years. By the time it is seen, it has been smoothed by time and space, stripped of urgency or immediacy. The sheer scale of a galaxy removes any sense of haste. No process within it aligns with human schedules. Birth, change, motion, and decay occur on timelines so extended that they feel almost still. This does not mean galaxies are inactive. Rather, their activity is distributed across time in a way that minimizes suddenness. The result is a system that is dynamic yet calm, immense yet balanced, vast without being overwhelming. Understanding the scale of a galaxy reveals a universe where size leads to patience, distance creates quiet, and time stretches events into gentle continuity rather than sharp moments. Galaxies exist in an environment where sound cannot travel. Sound requires a medium, such as air, water, or solid material, to carry pressure waves from one location to another. Interstellar and intergalactic space are far too sparse to serve this function. Even within a galaxy, the average density of matter is so low that sound waves cannot propagate in any meaningful way. As a result, all galactic activity occurs in complete silence. The space between stars inside a galaxy is not empty in an absolute sense, but it is extremely thin. Typical interstellar space contains only a few atoms per cubic centimeter, and in many regions even fewer. By comparison, Earth's atmosphere contains roughly 10-19 molecules per cubic centimeter at sea level. This enormous difference means that pressure waves dissipate almost instantly. Any vibration produced by stellar motion, explosions, or collisions simply does not transfer as sound. Stars move through galaxies without creating turbulence. There is no friction comparable to air resistance because there is almost nothing to push against. A star orbiting the galactic center passes through space without disturbing it in a way that would generate noise. Gas clouds drift, rotate, and slowly collapse under gravity, but this movement does not create audible effects. Motion exists, but it is mechanically silent. Even extremely energetic events do not produce sound in space. Supernovae release vast amounts of energy and eject material at high speeds, but this energy spreads outward as radiation and particle motion, not as pressure waves. Locally within the expanding debris cloud, particles collide and transfer energy, yet these interactions are isolated to tiny regions. Beyond those regions, the event remains silent. At galactic distances, supernovae are seen only as changes in light, never heard. Galactic collisions and mergers also occur without sound. When galaxies interact, their stars rarely collide because the distances between stars are so large. Gas clouds may compress and trigger star formation, but this compression happens slowly and quietly. Entire galaxies can pass through one another over hundreds of millions of years without producing anything analogous to noise. The process is defined by gravity and gradual redistribution of matter. There is also no background hum within a galaxy. On Earth, even quiet environments contain sound caused by air movement, mechanical vibrations, and biological activity. In a galaxy, none of these exist on a large scale. There is no wind, no rustling, no ambient vibration. The dominant forces are gravity and electromagnetic radiation, both of which operate without producing sound. This silence is constant and uninterrupted. It does not fluctuate between loud and quiet moments. Instead, it is an absolute absence of acoustic activity. A galaxy does not become noisy during periods of star formation or calm during quieter phases. From a physical standpoint, it is always silent. Change is expressed only through light, motion, and energy transfer that cannot be heard. The absence of sound also means there is no echo, resonance, or reverberation. Nothing carries vibrations from one region to another. Each event is isolated by distance and vacuum. Even regions that are relatively dense by cosmic standards remain far too thin to transmit sound waves effectively. This silent nature contributes to the long-term stability of galaxies. Without pressure-driven turbulence on large scales, motion remains orderly. Gas settles slowly, stars maintain predictable orbits, and structures persist for long periods. Silence is not merely a sensory absence. It reflects the physical conditions that allow galaxies to remain stable over billions of years. When studying galaxies, all information comes through light and other forms of radiation. Telescopes detect photons, not sound. The universe communicates visually and energetically, not acoustically. The silence of a galaxy is therefore not an artistic idea, but a direct consequence of the low density of matter and the fundamental laws of physics governing space. In this way, a galaxy exists as a vast, silent system where motion, change, and energy unfold without noise, vibration, or auditory disturbance, reinforcing the sense of calm created by its immense scale and emptiness. Spiral galaxies rotate, but their rotation is extremely slow when measured against human experience. A full rotation of a typical spiral galaxy takes hundreds of millions of years. For example, stars in a galaxy like the Milky Way complete one orbit around the galactic center in roughly 200 to 250 million years, depending on their distance from the center. This means that since the time complex life appeared on Earth, the Sun has completed only a small number of galactic orbits. This rotation does not resemble the spinning of a solid object. A galaxy is not rigid. Different regions rotate at different speeds, a pattern known as differential rotation. Stars closer to the center orbit faster, while those farther out move more slowly. Despite this variation, the overall structure of the galaxy remains stable over long periods. Spiral arms are not fixed material structures but density waves, regions where stars and gas become slightly more concentrated as they move through the galactic disk. Because of the immense scale involved, rotational motion appears almost frozen in time. Over a human lifetime, even precise measurements show only minuscule changes in stellar positions. Astronomers detect galactic rotation by observing shifts in light frequencies, not by watching stars visibly move. This illustrates how slow and steady the motion truly is. The forces driving galactic rotation are balanced. Gravity pulls stars inward toward the galactic center, while their orbital motion carries them forward. This balance prevents collapse and also prevents stars from flying away. The result is a long-lasting, repeating motion that can persist for billions of years without dramatic alteration. Gas and dust in the galactic disk follow similar rotational patterns. Large clouds of hydrogen rotate gently around the center, gradually evolving over time. These clouds may take tens of millions of years to noticeably change shape. Even when star formation occurs within them, it does not disrupt the overall rotation of the galaxy. The process fits smoothly into the existing motion. The rotation of spiral galaxies is so gradual that it distributes change evenly across time. There are no sudden accelerations or stops. Angular momentum, conserved from the galaxy's formation, continues to govern motion long after the initial collapse of matter. This conservation contributes to the predictable nature of galactic rotation. From a large-scale perspective, rotation contributes to a sense of order. Despite containing billions of independent objects, the galaxy behaves as a coherent system. Each star follows its own path, yet all paths align into a shared rotational pattern. This coordination does not require control or adjustment. It emerges naturally from gravitational laws acting over vast distances. Even disturbances such as passing satellite galaxies or internal starbursts rarely alter rotation significantly. The mass of a spiral galaxy is so large, and its timescale so long, that temporary disruptions are absorbed gradually. The disk may warp slightly or thicken over time, but rotation continues without interruption. Rotation also plays a role in shaping the appearance of spiral galaxies. The slow turning stretches material into broad, sweeping arms. Because this happens over immense timescales, the arms appear smooth and continuous rather than turbulent. The visual impression is one of gentle curvature rather than sharp motion. In physical terms, galactic rotation represents motion without urgency. Energy is distributed across enormous distances and long durations. Nothing spins rapidly enough to create instability on short timescales. Instead, rotation becomes a background condition of the galaxy, steady and reliable. Understanding the slow rotation of spiral galaxies reveals a universe where movement does not imply speed and change does not require immediacy. Rotation exists, but it unfolds so gradually that it reinforces stability rather than disturbance, contributing to the overall calm nature of galactic systems. Time within a galaxy operates on scales that are vastly longer than human perception. Most physical processes in galaxies occur over millions to billions of years, making human timeframes effectively negligible by comparison. This difference in scale is one of the primary reasons galactic activity feels unhurried. Events that seem significant astronomically unfold so slowly that, from a short-term viewpoint, they appear almost static. Galactic orbits are a clear example of extended timescales. A star located at a distance similar to the Sun's position from the center of a spiral galaxy requires roughly 200 million years to complete one orbit. Stars farther out take even longer. Over the course of a human lifetime, a star moves only an imperceptible fraction of its path. This means that galactic structure remains visually unchanged for thousands of generations. Star formation is also governed by long durations. Gas clouds drift and compress over tens of millions of years before forming stars. The collapse of a molecular cloud is slow because gravity must overcome internal pressure and rotation. Once stars form, they can remain stable for billions of years, especially low-mass stars. The life cycles of stars are measured not in years but in cosmic epochs. Galaxies themselves evolve slowly. Their overall shapes, spiral, elliptical, or irregular, persist for extremely long periods. While interactions and mergers do occur, these processes unfold over hundreds of millions or billions of years. Even when galaxies merge, the transformation is gradual rather than sudden. Stars adjust their orbits slowly as gravitational fields change. Human concepts such as deadlines, schedules, and urgency do not apply at galactic scales. There is no preferred moment for change. Physical laws operate continuously, without acceleration toward a goal. Gravity does not rush matter into stars, it draws it inward steadily. Radiation does not flare suddenly across a galaxy, it spreads outward at the constant speed of light. Because of these timescales, galaxies can be considered stable systems. Their large size smooths out short-term fluctuations. A single supernova, although energetic locally, has little effect on the galaxy as a whole. Over millions of years, many such events occur, but their influence blends into a steady background of energy and matter recycling. Even the motion of galaxies through space reflects extended time. Galaxies move relative to one another at speeds of hundreds of kilometers per second. Yet because distances are so vast, encounters take billions of years. From within a galaxy, this motion is undetectable without precise measurement. Nothing signals an approaching interaction until it is already well underway over cosmic timescales. The absence of urgency is reinforced by the predictability of physical laws. Gravity, electromagnetism, and nuclear processes behave the same way across time. There are no sudden shifts in how these forces operate. As a result, galactic evolution follows smooth trajectories rather than abrupt changes. From an observational standpoint, galaxies appear timeless. Ancient civilizations saw the same faint band of the Milky Way that is visible today. Over recorded history, its appearance has not changed in any noticeable way. This is not because nothing is happening, but because everything is happening too slowly to register on short timescales. Cosmic time also allows for balance. Matter cycles through stars, gas, and dust repeatedly over billions of years. Heavy elements formed in one generation of stars become part of the next. This recycling is continuous and unforced, shaped by gradual processes rather than sudden transformations. Understanding galactic time reveals that urgency is a feature of human systems, not cosmic ones. In galaxies, motion, change, and evolution are spread across such long durations that they produce continuity instead of disruption. Time itself becomes a stabilizing factor, ensuring that nothing needs to happen quickly for a galaxy to exist, function, and endure. Starlight within a galaxy is not concentrated into sharp points or intense beams when viewed on large scales. Instead, it is distributed gently across vast regions, creating a diffuse glow rather than focused brightness. This softness arises from the sheer number of stars and the immense distances between them. Each star emits light, but that light spreads outward in all directions, weakening as it travels. By the time it contributes to the overall appearance of a galaxy, it has become part of a broad, even illumination. In spiral galaxies, starlight is spread along the disk and spiral arms. These arms are regions where stars and gas are slightly more concentrated, not dense clusters packed together. Because of this, the light they produce appears as smooth, extended bands rather than sharp lines. The arms curve gradually, following the galaxy's rotation, and their brightness fades slowly toward the edges. There is no sudden change from bright to dark, only gradual transitions. Most of the light in a galaxy comes from ordinary stars similar to or smaller than the Sun. Extremely bright stars exist, but they are rare and short-lived. Their contribution to the galaxy's total light is limited by both their small numbers and the distances involved. Over time, the combined output of many stable, long-lived stars dominates the overall glow, producing consistency rather than variation. Interstellar dust also plays a role in softening galactic light. Dust grains absorb and scatter some of the light passing through them, reducing sharp contrasts. This scattering spreads light over wider angles, further smoothing the galaxy's appearance. Dust does not block light completely across large regions. Instead, it redistributes it, contributing to a gentle, diffuse effect. The distribution of starlight is influenced by the age of stars as well. Older stars tend to emit redder, less intense light than younger, massive stars. Galactic disks and bulges often contain large populations of older stars whose combined light is steady and subdued. This results in a warm, even glow rather than intense brightness. Because light travels at a finite speed, the starlight observed from a galaxy represents a mixture of different moments in time. Light from closer stars arrives sooner than light from more distant ones. However, these differences are measured in years or thousands of years within a single galaxy, which is negligible compared to galactic timescales. The result is a visually stable system where brightness does not fluctuate rapidly. On a physical level, starlight spreads out because space offers no mechanism to confine it. There are no walls, boundaries, or reflective surfaces. Photons travel freely until they are absorbed or scattered. This freedom ensures that light naturally becomes more diffuse as it moves away from its source. In a galaxy, with billions of sources emitting continuously, the combined effect is a smooth background of illumination. Even the brightest regions of galaxies do not overwhelm their surroundings. Star-forming regions can appear brighter locally, but they occupy small fractions of the galaxy's total area. Their light blends into the surrounding glow over distance. The overall balance remains intact, with no single region dominating the visual impression for long. The soft spread of starlight also reflects energy balance. Stars convert nuclear energy into light at steady rates over long periods. Sudden bursts of energy are rare and localized. Most energy output is continuous and predictable, contributing to long-term consistency and brightness. When galaxies are observed from great distances, individual stars can no longer be resolved. Their light merges completely into a unified glow. This reinforces the perception of calm, as variations disappear and only averaged light remains. The galaxy becomes a single, coherent source rather than a collection of distinct points. In this way, the distribution of starlight across a galaxy is a direct consequence of scale, distance, and physical laws. Light spreads, softens, and blends over time and space, producing an appearance defined by gradual change and stability rather than sharp intensity or sudden contrast. Gravity is the primary force that holds a galaxy together, yet it operates without tension, strain, or sudden acceleration. In a galaxy, gravity acts over enormous distances, linking stars, gas, dust, and dark matter into a single, bound system. Because the mass of a galaxy is spread across vast volumes of space, gravitational influence is distributed smoothly rather than concentrated into violent pulls. Each star in a galaxy follows an orbit determined by the combined gravitational effects of all surrounding mass. No single object dominates this force except near the galactic center. Even there, gravity changes gradually with distance. This creates stable orbits that can persist for billions of years. Stars do not fall inward rapidly, nor are they flung outward suddenly. Their motion is balanced and repetitive. The smoothness of galactic gravity comes from scale. On small scales, such as within planetary systems, gravity can cause noticeable acceleration over short periods. On galactic scales, distances are so large that changes occur slowly. A star responds to gravitational forces over millions of years, not seconds. This results in motion that appears calm and continuous. Dark matter contributes significantly to this stability. Although it does not emit light or interact electromagnetically, it adds mass to the galaxy. Dark matter forms an extended halo that surrounds the visible galaxy, providing additional gravitational support. This halo prevents stars in the outer regions from drifting away and helps maintain orderly rotation. Its influence is constant and silent, reinforcing long-term balance. Gas and dust clouds are also governed by gravity, but they respond gently. Large clouds drift and rotate, gradually changing shape as gravity slowly compresses them. Internal pressures counteract collapse, creating equilibrium states that can last millions of years. When collapse does occur, it happens in localized regions without disrupting the galaxy as a whole. Gravitational interactions between stars inside a galaxy are rare. Because stars are separated by vast distances, close encounters almost never occur. Most stars move as if they are alone, responding to the overall gravitational field rather than to nearby neighbors. This reduces chaos and enhances predictability within the system. Even when galaxies interact with one another, gravity acts gradually. Tidal forces stretch and distort shapes over long timescales. Stars adjust their orbits slowly, and gas responds by forming new structures. There is no sudden collapse or explosive rearrangement on a galactic scale. Change unfolds over hundreds of millions of years. Gravity does not weaken abruptly within a galaxy. Its influence tapers smoothly with distance. This gradual change prevents sharp boundaries or unstable regions. Matter remains bound in extended orbits, creating diffuse edges rather than rigid limits. The galaxy transitions naturally into surrounding space. From an energy perspective, galactic gravity conserves motion. Angular momentum remains largely constant over time. This conservation prevents rapid contraction or expansion. The galaxy settles into a stable configuration early in its life and maintains it with only slow evolution. Because gravity operates predictably and continuously, it creates a sense of order without effort. There is no requirement for adjustment, correction, or intervention. Physical laws apply uniformly, allowing the galaxy to maintain structure through simple balance rather than forceful containment. Understanding how gravity holds a galaxy together reveals that stability does not require rigidity. Instead, it emerges from distributed mass, vast distances, and long timescales. Gravity's gentle influence ensures that billions of objects can coexist in motion without collision, tension, or instability, sustaining the galaxy in a state of enduring equilibrium. Inside a galaxy, the space between stars is vast and largely empty. Even though galaxies contain billions of stars, they are spread across such immense volumes that direct interactions are extremely rare. In regions near the Sun, the average distance to the nearest star is a little over 4 light years. This separation means that most of a galaxy consists of open space rather than matter. Interstellar space is not a perfect vacuum, but it is close. It contains small amounts of gas, mostly hydrogen and helium, along with traces of heavier elements and dust. Typical densities range from a few atoms per cubic centimeter down to far less in quieter regions. These densities are so low that matter behaves differently than it does in everyday environments. Particles travel long distances without colliding, and energy spreads slowly. This emptiness plays a major role in the calm behavior of galaxies. With so little material present, there is minimal friction. Objects move freely without resistance. Stars orbit the galactic center without losing energy to surrounding matter. Gas clouds drift without turbulence on large scales. Motion persists smoothly over long periods. The emptiness also prevents frequent collisions. Despite the large number of stars, the probability of two stars colliding in a typical galaxy is extremely low. Calculations show that even over billions of years, most stars will never experience a close encounter with another star. This allows stellar systems, including planetary systems, to remain stable for long durations. Interstellar gas occupies only a tiny fraction of galactic volume. Even large molecular clouds, which are the densest regions in galaxies, are sparse compared to Earth's atmosphere. Within these clouds, gravity can slowly gather material, but outside them, space remains quiet and unchanged. The contrast between dense regions and empty regions emphasizes how much of a galaxy is inactive at any given moment. Light also travels mostly through emptiness. Photons emitted by stars can travel for years, centuries, or longer without interacting with anything. This uninterrupted travel contributes to the clarity and consistency of astronomical observations. It also means that energy moves without disturbance, spreading evenly rather than creating localized agitation. The emptiness inside galaxies allows for thermal stability. Heat does not transfer easily because particles are too far apart to collide frequently. As a result, regions can remain cold or warm for long times without sudden shifts. Temperatures change slowly, governed by radiation rather than conduction or convection. From a structural perspective, emptiness provides flexibility. The galaxy can adjust gradually to changes in mass distribution or external influences. If a small satellite galaxy passes nearby, its gravitational effect propagates through the galaxy slowly. Stars respond over millions of years, altering their orbits slightly without causing widespread disruption. The calm nature of galactic interiors is therefore not accidental. It arises directly from low density and large separation. Matter exists, but it is thinly distributed. Energy is present, but it spreads quietly. Motion occurs, but it is unforced. When considering a galaxy as a whole, it becomes clear that emptiness is not absence, but a defining feature. It allows structure to exist without pressure, motion without noise, and change without urgency. The vast spaces between stars act as buffers, ensuring that local events remain local and that the galaxy maintains long-term stability. This immense internal emptiness is one of the key reasons galaxies endure for billions of years. With few collisions, little friction, and minimal disturbance, their components can follow predictable paths. The result is a system dominated not by activity, but by continuity, where most of the galaxy remains quiet at all times. Within a galaxy, darkness occupies far more volume than light. Although galaxies contain billions of stars, those stars emit light from relatively small points in space. the regions between them remain largely unlit. Because light spreads outward and weakens with distance, most of a galaxy's interior exists at extremely low light levels. Even near stars, illumination drops rapidly as distance increases. The human eye associates darkness with absence, but in a galactic context, darkness is simply the natural state of space. Light does not fill space evenly. It travels in straight paths until it encounters matter. In the absence of dense material, photons pass through without scattering. As a result, vast regions between stars remain dark despite being surrounded by luminous objects. Most stars are not bright enough to illuminate large areas. A star like the Sun provides significant light only within a relatively small region. Beyond a few astronomical units, illumination decreases sharply. At distances of light years, the contribution of an individual star becomes negligible. In a galaxy, where stars are separated by several light years, their light rarely overlaps strongly enough to brighten the surrounding space. Even in the densest parts of galaxies, darkness dominates. Galactic cores may contain higher concentrations of stars, but the volume between them is still immense. Light from many stars overlaps slightly, producing a faint glow, but this glow remains subdued. There is no widespread brightness filling the space between stars. Instead, light exists as a sparse background against a much larger dark environment. Interstellar dust also contributes to the dominance of darkness. Dust grains absorb and scatter light, preventing it from traveling freely across long distances. While this dust can reflect or re-emit light at longer wavelengths, it reduces visible brightness. This process further limits how far starlight can illuminate space, reinforcing the prevalence of darkness. Darkness in galaxies is also linked to energy distribution. Stars emit energy at specific rates determined by nuclear processes in their cores. This energy output is finite and localized. As photons spread outward, their energy is distributed over larger areas, lowering intensity. There is no mechanism to concentrate light across vast regions without dense sources. From a physical standpoint, darkness is the default condition because matter is sparse. Light requires sources, and sources are discrete. Between those sources, space remains largely unaffected. This is why even galaxies filled with stars appear faint and translucent when observed from great distances. Their light is diluted across enormous volumes. The dominance of darkness has stabilizing effects. Without constant radiation pressure or intense illumination, most regions remain thermally quiet. Temperatures change slowly, influenced primarily by distant radiation rather than nearby sources. This thermal calm supports the long-term persistence of galactic structures. Darkness also allows for clear separation of events. A burst of light from a star-forming region does not overwhelm the rest of the galaxy. Its influence fades with distance. The surrounding darkness absorbs no energy and exerts no reaction. Events remain localized, and the galaxy as a whole remains unchanged. On observational timescales, the darkness within galaxies appears constant. While stars age and new ones form, the overall balance between light and dark remains stable. No process exists that would suddenly flood a galaxy with light. Brightness increases and decreases only gradually over cosmic time. Understanding why darkness dominates galaxies reveals a system governed by spacing, distance, and finite energy. Light exists, but it is limited. Darkness fills the rest. This balance ensures that galaxies remain visually and physically calm, defined more by vast quiet regions than by points of brightness. Interstellar dust is a minor component of a galaxy by mass, yet it plays a noticeable role in shaping galactic environments. Dust consists of tiny solid particles made primarily of carbon, silicates, ice, and heavier elements formed inside earlier generations of stars. These particles are extremely small, typically comparable in size to smoke particles or smaller. Despite their small size, they are spread across vast regions of a galaxy. Dust drifts through interstellar space at very low densities. Even in regions considered dusty, the total mass of dust is negligible compared to stars or gas. Most of a galaxy's dust is mixed thinly with interstellar gas, forming what is known as the interstellar medium. This medium fills the spaces between stars but remains highly diffuse. The motion of interstellar dust is slow and unforced. Dust grains respond primarily to gravity and, to a lesser extent, to radiation pressure from starlight. Because forces are weak and distances are large, dust moves gradually. Changes in position occur over thousands to millions of years. There is no rapid flow or turbulence on large scales. Dust does not clump easily on its own. Individual grains rarely collide because of the low density of space. When collisions do occur, they are gentle. Over long periods, dust can collect within larger gas clouds, but this process is gradual and localized. Outside of these regions, dust remains dispersed and calm. One of the main physical effects of dust is its interaction with light. Dust grains absorb and scatter starlight, especially at shorter wavelengths. This interaction does not create brightness, it reduces contrast. Light passing through dusty regions becomes dimmer and redder. This effect contributes to the soft appearance of galaxies rather than sharp brightness. Dust also emits energy, but very slowly. After absorbing light, dust grains re-radiate energy at longer wavelengths, primarily in the infrared. This emission is weak and spread over time. It does not create flashes or sudden changes. Instead, it contributes to a steady background glow detectable only with sensitive instruments. The presence of dust helps regulate temperatures within galaxies. By absorbing and re-emitting radiation, dust moderates energy flow. This process prevents extreme heating in many regions and supports long-term thermal balance. Dust does not trap heat aggressively. It releases energy gradually, maintaining equilibrium rather than instability. Interstellar dust is replenished and destroyed slowly. It forms in the outer layers of aging stars and in supernova remnants, then disperses into space. Over time, some dust grains are destroyed by radiation or shocks, while others survive and continue drifting. This cycle unfolds over millions of years and does not disrupt galactic structure. Because dust is spread so thinly, it does not impede motion. Stars pass through dusty regions without resistance. Gas clouds drift alongside dust with minimal interaction. The galaxy remains dynamically calm, with dust acting as a passive component rather than an active force. From a large-scale perspective, dust traces galactic structure without controlling it. Dust lanes often outline spiral arms because gas density is slightly higher there. These lanes are not signs of congestion or pressure, but of gradual accumulation over time. The dust highlights where processes are occurring slowly, not where sudden activity dominates. Interstellar dust contributes to the quiet character of galaxies by softening light, moderating energy, and moving without urgency. It does not announce its presence through force or motion. Instead, it exists as a thin, drifting component, reinforcing the overall stillness and continuity of galactic environments. Stars form inside galaxies through processes that are slow, gradual, and regulated by physical balance rather than sudden collapse. The primary locations of star formation are molecular clouds, which are large regions of relatively dense gas, and dust composed mostly of molecular hydrogen. Even though these clouds are denser than surrounding interstellar space, they are still extremely diffuse compared to everyday environments on Earth. Molecular clouds can span tens to hundreds of light years and contain enough material to form thousands or even millions of stars. Despite this potential, most of the material inside a molecular cloud does not immediately form stars. Gravity works continuously to pull matter inward, but it is counteracted by internal pressure, magnetic fields, and slow rotation within the cloud. These opposing influences prevent rapid collapse and keep the cloud in a long-lasting, stable state. The process of star formation begins only in small regions, where local conditions allow gravity to dominate slightly. These regions, called dense cores, develop gradually as gas drifts inward over long periods. The accumulation of matter happens quietly, without sharp boundaries or violent motion. Gas particles move slowly, colliding infrequently, and losing energy over millions of years before meaningful compression occurs. Even once a dense core begins collapsing, the process remains slow by human standards. The gravitational contraction of a star-forming core typically takes hundreds of thousands to several million years. During this time, material falls inward steadily rather than suddenly. The forming star increases in temperature and density gradually as gravitational energy is converted into heat. Star formation is inefficient. Only a small fraction of a molecular cloud's mass ever becomes stars. Much of the gas remains dispersed or is returned to interstellar space over time. This inefficiency contributes to the calm nature of galaxies, as it prevents rapid depletion of material and avoids bursts of excessive activity across large regions. External triggers for star formation, such as shock waves from nearby supernovae or interactions between gas clouds, also operate slowly at galactic scales. These influences compress gas gently rather than violently. The effects propagate gradually, altering conditions over long timescales instead of causing immediate, widespread collapse. Once nuclear fusion begins in a newly formed star, the surrounding region stabilizes. Radiation and stellar winds may push away nearby gas, but this happens progressively. The energy output of young stars unfolds over thousands to millions of years, giving the surrounding environment time to adjust without disruption. Across an entire galaxy, star formation proceeds at a measured pace. Even galaxies considered active form only a few stars per year on average. When spread across billions of stars and vast volumes, this rate represents a low level of change. The majority of a galaxy remains unaffected by star formation at any given time. This slow pace ensures continuity. New stars appear without altering the overall structure of the galaxy. Spiral arms persist, orbits remain stable, and gravitational balance is preserved. Star formation adds to the galaxy gradually, reinforcing long-term evolution rather than creating abrupt transformation. From a physical perspective, the calmness of star formation arises from the interplay of gravity, pressure, and time. No single force dominates instantly. Instead, equilibrium governs motion until slight imbalances allow slow progression. The result is a process that unfolds quietly within molecular clouds, contributing to the steady, enduring nature of galaxies rather than interrupting it. Star formation inside galaxies unfolds over extremely long timescales, shaped by gradual physical processes rather than rapid change. Even after a molecular cloud begins forming dense regions, the path from diffuse gas to a fully formed star is measured in millions of years. This extended duration is a direct consequence of low densities, large distances, and competing forces that regulate collapse. The earliest stage of star formation involves the slow accumulation of gas within a molecular cloud. Gravity pulls particles inward, but internal gas pressure, turbulence, and magnetic fields resist compression. These opposing forces reduce the rate at which matter can concentrate. As a result, gas moves inward at slow speeds, often only a few hundred meters per second or less. Over time, this gentle inward drift gradually increases density. Dense cores form within molecular clouds only after long periods of gradual change. These cores are small compared to the parent cloud and represent localized regions where gravity slightly outweighs opposing forces. Even then, collapse is not immediate. The core must cool by radiating energy, allowing gravity to continue drawing material inward. Cooling itself is slow because energy escapes primarily through radiation rather than direct contact between particles. Once collapse proceeds, the formation of a protostar takes hundreds of thousands of years. During this phase, material falls inward along wide, spiraling paths rather than plunging straight to the center. Angular momentum prevents rapid collapse, spreading the process across time. Accretion disks form around the developing star, and material settles gradually. After nuclear fusion begins in the core, the star does not instantly reach stability. It undergoes further adjustment as internal pressure balances gravity. This stage can last millions of years for low-mass stars. Throughout this period, energy output changes slowly, and the surrounding environment responds gradually. The long timescales of star formation ensure that galaxies do not change abruptly. Even in regions where many stars are forming, the process is spread out. Different stars begin and complete formation at different times. There is no synchronized burst across large areas. This staggering distributes energy and matter evenly, preserving galactic calm. Mass plays a key role in timing. High-mass stars form more quickly than low-mass stars, but they are rare. The majority of stars in galaxies are low-mass, long-lived stars that form slowly and persist for billions of years. Their dominance further slows the overall pace of change within galaxies. Star formation efficiency remains low across time. Large molecular clouds can exist for tens of millions of years, while forming only a small number of stars. Much of their material remains unused or returns to interstellar space. This inefficiency prevents rapid transformation of galactic gas into stars, maintaining long-term stability. The extended timescales also allow feedback processes to remain moderate. Radiation and winds from young stars influence nearby gas gradually. They disperse material over millions of years rather than causing immediate disruption. This controlled interaction allows star formation to regulate itself without destabilizing the surrounding region. Across an entire galaxy, the cumulative effect of slow star formation is continuity rather than change. Over billions of years, stars steadily appear, but the overall appearance of the galaxy evolves gently. Spiral patterns persist, mass distribution remains balanced, and gravitational structure is preserved. These long timescales demonstrate that star formation is not an urgent or explosive process on galactic scales. It is a slow conversion of diffuse matter into stable objects, governed by physics that favors patience and balance. This measured progression is a key reason galaxies remain calm, enduring systems across cosmic time. Stars within a galaxy follow stable orbits that persist for extremely long periods. Once a star forms and settles into motion around the galactic center, its path is largely determined by the combined gravitational influence of the galaxy's mass. These orbits are not temporary or chaotic. They are maintained over hundreds of millions to billions of years with minimal change. A star's orbit is shaped by the smooth gravitational potential of the galaxy, rather than by close interactions with other stars. Because stars are widely separated, direct gravitational encounters between individual stars are rare. Most stars respond to the averaged gravitational field, created by billions of other objects and dark matter. This averaging effect smooths motion and prevents sudden deviations. Orbital paths in galaxies are not perfect circles, but they are generally stable and predictable. Stars move along slightly elliptical orbits that repeat over long timescales. Variations in orbital shape occur slowly, influenced by gradual changes in mass distribution or weak tidal effects. These variations do not lead to instability or rapid reorganization. The conservation of angular momentum plays a central role in orbital stability. Once a star acquires its motion during galaxy formation, that motion persists unless acted upon by an external force. Because forces change slowly and encounters are rare, angular momentum remains nearly constant for most stars. This conservation ensures continuity in motion. Stars at different distances from the galactic center have different orbital periods. Inner stars complete orbits more quickly, while outer stars move more slowly. Despite this differential motion, the overall structure remains intact. The galaxy does not tear itself apart because gravitational forces and rotational motion remain balanced. Vertical motion, meaning movement above and below the galactic plane, is also stable. Stars oscillate gently around the disk plane over tens of millions of years. These oscillations are small and regular, adding to the overall predictability of stellar motion. They do not grow larger over time, which would indicate instability. The presence of dark matter further stabilizes stellar orbits. The dark matter halo extends well beyond the visible disk and contributes most of the galaxy's mass. Its gravitational influence creates a deeper potential well that holds stars in place, especially in the outer regions. Without this halo, many stars would gradually drift away. Over very long timescales, orbits can slowly change due to cumulative effects such as interactions with spiral density waves or weak tidal influences from nearby galaxies. However, these changes occur gradually. A star's basic orbital character remains intact for billions of years. From a galactic perspective, the stability of stellar orbits means that the overall appearance of the galaxy remains consistent. Stars do not migrate rapidly or unpredictably. The disk, bulge, and halo maintain their general structure. This persistence contributes to the sense of timelessness associated with galaxies. Stable orbits also allow complex systems, including planetary systems, to exist over long durations. The calm gravitational environment of a galaxy provides a reliable framework in which stars can host planets without constant disruption. This stability is a direct result of the smooth, long-term nature of galactic gravity. In summary, stars remain in stable orbits for millions to billions of years because gravitational forces act gently, interactions are rare, and angular momentum is conserved. This enduring stability is a fundamental characteristic of galaxies, ensuring that motion unfolds as repetition rather than disturbance across galactic space at speeds that are large in absolute terms, but extremely gentle when measured against cosmic timescales. Their motion is not abrupt or directional in the way movement is experienced on Earth. Instead, it unfolds gradually, shaped by gravity acting over millions and billions of years. A galaxy may travel hundreds of kilometers per second relative to others, yet this speed is spread across distances so vast that the movement feels almost imperceptible when observed from within the universe itself. Intergalactic space is not completely empty, but it is extraordinarily sparse. Between galaxies, there are only a few atoms per cubic meter, far fewer than the best vacuums created on Earth. As galaxies drift through this near-emptiness, there is little resistance. No friction slows them down in a mechanical sense. Their paths are guided primarily by gravitational influences from nearby galaxies, galaxy groups, and massive structures such as clusters and filaments. Most galaxies are not isolated. They are part of gravitationally bound systems called galaxy groups or clusters. Within these structures, galaxies move in slow orbits around a shared center of mass. These orbits are not sharply defined like planets around a star. They are broad, elongated paths that can take billions of years to complete a single cycle. From a human perspective, a galaxy's position within its group appears almost fixed. On even larger scales, galaxies participate in the expansion of the universe itself. As space expands, the average distance between distant galaxies increases over time. This expansion is not caused by galaxies moving through space in a conventional way, but by space itself stretching. Galaxies embedded in this expanding space are carried along smoothly, without acceleration that would be felt internally. Inside a galaxy, stars remain gravitationally bound and unaffected by this expansion. The motion of galaxies through intergalactic space is remarkably orderly. Large surveys show that galaxies trace long, thread-like structures known as cosmic filaments, separated by vast voids. Over billions of years, galaxies drift along these filaments toward regions of slightly higher gravitational density. This movement is slow and continuous, with no sudden changes in direction. Even when galaxies approach one another, interaction is rare on short timescales. The average distance between galaxies is so large that direct encounters are uncommon. When interactions do occur, they unfold over hundreds of millions of years. Long before any visible change takes place, the galaxies have already been influencing each other gravitationally for immense periods of time. From within a galaxy, this motion is almost impossible to perceive. Stars continue their stable orbits, gas clouds drift slowly, and planetary systems remain unaffected. There is no sensation of travel, no vibration, and no reference point that would reveal the galaxy's gradual journey through space. The motion exists on scales far beyond everyday experience. Because of these immense timescales and distances, galaxies can be described as drifting rather than traveling. Their movement is steady, predictable, and calm, governed by gravity and the large-scale structure of the universe. Over billions of years, a galaxy may change its position relative to others, but at any given moment, it appears nearly still. This slow movement through intergalactic space contributes to the sense of stability associated with galaxies. Nothing about their motion suggests urgency or acceleration. Instead, it reflects a universe where change happens gradually, without sudden transitions. The paths galaxies follow are shaped long before they are completed, and they continue along them without interruption. In this way, galaxies exist as quiet participants in a vast, slowly evolving cosmos. Their motion is constant yet gentle, ongoing yet unhurried, unfolding across spans of time so long that stillness and movement become almost indistinguishable. Galaxies are immense systems separated by distances so large that direct interactions between them are uncommon. Although the universe contains hundreds of billions of galaxies, the average spacing between them is vast. In many regions, millions of light-years of mostly empty space lie between one galaxy and the next. This separation plays a central role in why galaxies rarely interact despite their size. A typical large galaxy may span tens or even hundreds of thousands of light-years across. While this seems enormous, the distance to the nearest neighboring galaxy is often several times greater than the galaxy's own diameter. For example, galaxies within the same group may still be separated by hundreds of thousands or millions of light years. On larger scales, galaxies outside local groups are even farther apart, separated by expanding space itself. The universe is structured in a way that naturally limits frequent encounters. Galaxies are arranged along filaments and clusters, with large voids in between. Within these filaments, galaxies follow slow, stable paths shaped by gravity. Their trajectories rarely cross closely enough for collisions to occur. Most galaxies move in roughly parallel flows determined by the large-scale distribution of mass, which reduces the likelihood of direct contact. Gravity governs galactic motion, but its influence weakens with distance. While galaxies exert gravitational forces on one another, those forces are typically too small to significantly alter paths unless galaxies come relatively close. Because of the immense separations involved, most galaxies feel only mild gravitational effects from their neighbors. These effects accumulate slowly and rarely result in dramatic interactions. When galaxies do interact, the process is extremely gradual. Long before stars or gas clouds are affected, the galaxies have been influencing each other for hundreds of millions of years. Tidal forces slowly distort their shapes, gently stretching arms of stars and gas. Even in these cases, the interaction is not sudden or violent on short timescales. It unfolds so slowly that a single moment appears almost unchanged from the last. Another reason interactions are rare is the expansion of the universe. On large scales, space itself is expanding, increasing the distance between galaxies that are not gravitationally bound. This expansion counteracts the pull of gravity between distant galaxies, preventing many potential encounters. As time passes, galaxies outside clusters tend to drift farther apart rather than toward each other. Within galaxy clusters, interactions are more likely, but even there, they are infrequent compared to the size and age of the universe. Clusters contain hundreds or thousands of galaxies, yet the volume they occupy is still enormous. Galaxies move through clusters on wide orbits, often passing by one another at large distances. Close encounters remain the exception rather than the rule. Despite their rarity, galactic interactions are well studied because they leave long-lasting traces. Streams of stars, distorted shapes, and extended halos can remain visible for billions of years after an interaction begins. The persistence of these features makes encounters seem more common than they actually are. In reality, each visible interaction represents a very long process that occupies only a small fraction of a galaxy's total lifetime. For most galaxies, the majority of their existence passes without significant external disturbance. Stars form, age, and fade, while the galaxy continues its slow motion through space, largely unaffected by its neighbors. The galaxy's structure remains stable, shaped more by internal processes than by external encounters. This rarity of interaction contributes to the overall calmness of the universe on large scales. Galaxies evolve quietly, separated by immense distances, following predictable paths defined by gravity and expansion. Their isolation allows them to persist for billions of years without interruption, reinforcing the sense of continuity and stillness that characterizes the cosmic environment. Dark matter plays a central role in the structure and stability of galaxies, even though it does not emit, absorb, or reflect light. Its presence is inferred through its gravitational effects rather than direct observation. Measurements of galactic motion consistently show that the visible matter alone, stars, gas, and dust, is not sufficient to account for the way galaxies behave. The additional gravitational influence required to explain these motions is attributed to dark matter. One of the clearest pieces of evidence for dark matter comes from the way galaxies rotate. In spiral galaxies, stars far from the center orbit at speeds similar to those much closer in. According to classical gravitational expectations, outer stars should move more slowly if only visible matter were present. Instead, their steady speeds indicate the presence of a large, unseen mass surrounding the galaxy. This mass forms an extended halo that envelops the visible disk. Dark matter halos are much larger than the luminous parts of galaxies. While a galaxy's stars may be concentrated within a region tens of thousands of light years across, its dark matter halo can extend several times farther. This halo provides a gravitational framework that holds the galaxy together. Without it, many galaxies would not be able to maintain their current shapes or remain gravitationally bound. Within this framework, stars and gas move along stable paths. The gravitational influence of dark matter smooths out variations in motion, reducing the likelihood of rapid structural changes. Over long periods, this contributes to the overall calmness of galactic evolution. The galaxy does not rely solely on its visible mass to remain intact. Instead, it is supported by a much larger, evenly distributed gravitational field. Dark matter also affects how galaxies form in the first place. In the early universe, regions with slightly higher concentrations of dark matter began to attract ordinary matter. Gas accumulated within these dark matter structures, gradually cooling and forming stars. The resulting galaxies grew within pre-existing dark matter halos, which shaped their size and distribution from the beginning. On larger scales, dark matter influences how galaxies are arranged across the universe. It forms a vast network of filaments and dense regions that guide the motion of galaxies over billions of years. Visible matter follows this underlying structure, settling into the gravitational wells created by dark matter. This process occurs slowly and predictably, without sudden changes. Despite its significant role, dark matter interacts very weakly with ordinary matter aside from gravity. It does not collide, clump, or dissipate energy in the way gas does. This lack of interaction contributes to its stability. Dark matter halos remain relatively unchanged over long periods, providing a consistent gravitational environment for galaxies to exist within. Because dark matter does not participate in processes like star formation or radiation emission, it remains unaffected by the internal evolution of galaxies. Stars may form, explode, or fade, but the surrounding dark matter halo persists. This continuity helps explain why galaxies can remain stable for billions of years, even as their visible components change. In galaxy clusters, dark matter plays a similar stabilizing role on an even larger scale. The combined dark matter of many galaxies creates a deep gravitational well that binds the cluster together. Galaxies move within this shared structure on slow, extended paths, rarely experiencing abrupt changes in motion. Overall, dark matter acts as a quiet, constant presence in the universe. Its influence is steady rather than dramatic, shaping galaxies without drawing attention to itself. By providing the gravitational support necessary for stability, dark matter allows galaxies to exist as long-lived, orderly systems, evolving gradually within a calm and enduring cosmic framework. Galactic evolution occurs over extremely long timescales, shaped by processes that unfold gradually rather than through sudden change. From their formation in the early universe to their present states, galaxies evolve in ways that are slow, cumulative, and often subtle. Most of the changes that define a galaxy's history take hundreds of millions to billions of years to become noticeable. One of the primary drivers of galactic evolution is star formation. Gas within galaxies cools and condenses slowly, forming stars over extended periods. This process is regulated by gravity, pressure, and energy feedback from existing stars. Rather than consuming all available gas at once, galaxies typically convert it into stars at a steady pace, allowing star formation to continue for long spans of time. As stars age, they return material to the interstellar medium through stellar winds and, in some cases, supernova explosions. Even these events, while energetic on local scales, contribute to long-term, gradual evolution when considered across an entire galaxy. The recycled material mixes with existing gas and can eventually form new generations of stars, continuing the cycle without abrupt global disruption. Galaxies also evolve through slow changes in structure. Spiral arms, bars, and disks can form or fade over billions of years as stars and gas respond to gravitational forces. These features are not static, but their transformations are gentle and continuous. The overall shape of a galaxy typically remains recognizable for very long periods, even as internal details shift. Interactions with other galaxies can influence evolution, but these interactions are usually drawn out. When galaxies pass near one another, gravitational effects develop gradually. Tidal forces slowly reshape their outer regions, and any resulting changes unfold over immense timescales. Even mergers, which represent some of the most significant evolutionary events, progress over hundreds of millions of years from initial approach to final settling. Environmental factors also play a role in gradual evolution. Galaxies within clusters may slowly lose gas as they move through hot intracluster environments. This process, known as ram pressure stripping, occurs over extended periods and affects star formation rates rather than causing immediate structural collapse. The galaxy adjusts slowly to its changing surroundings. Chemical evolution within galaxies is another long-term process. As generations of stars form and die, heavier elements are produced and dispersed into the interstellar medium. The overall composition of a galaxy changes incrementally, with metallicity increasing over billions of years. This gradual enrichment influences future star and planet formation without sudden transitions. The influence of dark matter further stabilizes galactic evolution. Dark matter halos provide a consistent gravitational framework that limits rapid structural change. Within this framework, visible matter evolves at a measured pace, responding smoothly to internal and external influences. On the largest scales, the expansion of the universe shapes galactic evolution by increasing distances between unbound galaxies. This expansion reduces the frequency of interactions over time, allowing many galaxies to evolve in relative isolation. As a result, long periods of stability become the dominant feature of galactic history. Overall, galactic evolution is characterized by continuity rather than disruption. Changes accumulate slowly, guided by well-understood physical processes. From star formation to structural adjustment, each step unfolds at a pace that emphasizes persistence and balance. The result is a universe in which galaxies change quietly, maintaining coherence and stability across vast spans of cosmic time. Stars within a galaxy age in a predictable and gradual manner, following physical processes that are well understood and consistent across the universe. A star's lifetime is determined primarily by its mass. Smaller stars burn their fuel slowly, while larger stars consume it more quickly. This difference creates a wide range of stellar lifespans, from millions to trillions of years, contributing to the long-term stability of a galaxy. Most stars in a galaxy are low-mass stars. These stars fuse hydrogen into helium at a slow rate, producing steady energy over extremely long periods. Red dwarf stars, which are the most common type, can remain active for hundreds of billions to trillions of years. Because of their longevity, they dominate the stellar population of galaxies over cosmic time, ensuring that galaxies remain luminous and structurally stable far into the future. As stars age, their internal fuel gradually changes. In the early stages, hydrogen fusion provides a stable source of energy that balances gravitational collapse. Over time, hydrogen in the core is depleted, and the star begins to fuse heavier elements, depending on its mass. These transitions occur slowly, often over millions or billions of years, without sudden changes in brightness or behavior on short timescales. In galaxies like the Milky Way, many stars are already billions of years old. These older stars tend to be found in galactic bulges and halos, where star formation occurred early in the galaxy's history. Their light is steady and predictable, contributing to the soft, consistent glow seen in many galaxies. Because these stars evolve slowly, the overall appearance of the galaxy changes very little over long periods. When stars reach the final stages of their lives, they return material to the galaxy. Low and medium-mass stars gently shed their outer layers, forming planetary nebulae and leaving behind dense remnants such as white dwarfs. This process is gradual and localized. It does not disturb the galaxy as a whole, but instead enriches the surrounding space with elements created during the star's lifetime. More massive stars end their lives as supernovae, releasing energy and heavy elements into the interstellar medium. While supernovae are intense events on small scales, they are rare when considered across an entire galaxy. Their effects are spread out over vast distances and long times, contributing to chemical enrichment rather than widespread disruption. Over millions of years, the material they release becomes part of new stars, continuing the cycle. As a galaxy ages, its overall star formation rate often declines. Gas supplies slowly decrease, and fewer new stars are formed. The stellar population gradually shifts toward older, longer-lived stars. This transition happens over billions of years and gives many mature galaxies a stable, settled appearance. The change is subtle, noticeable only when comparing galaxies at very different stages of cosmic history. Throughout this process, the motion of stars remains calm and orderly. Aging does not significantly alter a star's orbit within the galaxy. Stars continue to follow a stable path shaped by the galaxy's gravitational structure, largely unaffected by their internal evolution. This consistency helps maintain the galaxy's overall balance and shape. The peaceful aging of stars reflects the broader nature of galactic time. Individual stars change slowly, and their collective evolution unfolds without urgency. Galaxies persist as long-lived systems where stellar birth, aging, and death occur continuously, but gently, reinforcing a sense of continuity that spans billions of years. Most galaxies appear unchanged across the span of human history, because the processes that alter their structure and appearance operate on timescales far longer than human observation. Human history covers only a few thousand years, while galaxies evolve over billions of years. When compared to these immense durations, the period during which humans have observed the sky represents only a brief moment. The positions of stars within a galaxy shift continuously, but these changes are extremely small over short times. Stars orbit the galactic center at speeds of hundreds of kilometers per second. Yet the distances involved are so vast that their movement across the sky is nearly imperceptible without precise measurement over long intervals. As a result, the overall pattern of a galaxy appears stable from one human generation to the next. Star formation and stellar death also contribute little visible change on short timescales. While new stars are constantly forming and older stars are aging, the total number of stars in a large galaxy is so great that individual changes do not noticeably affect its appearance. The birth or death of even many thousands of stars represents a negligible fraction of the galaxy's total stellar population. Large-scale galactic features such as spiral arms, disks, and bulges persist for hundreds of millions to billions of years. Although these structures are not completely fixed, their evolution is gradual. Spiral arms, for example, are long-lived patterns shaped by gravitational density waves rather than permanent collections of specific stars. This allows the overall spiral shape to remain recognizable over extremely long periods. Galactic interactions, which can significantly alter a galaxy's appearance, are rare on human timescales. Even when galaxies are in the early stages of interaction, visible changes develop slowly. Tidal distortions, extended arms, and mergers unfold over hundreds of millions of years. From a human perspective, a galaxy involved in such a process appears almost static. The expansion of the universe also contributes to this apparent stability. For galaxies that are not gravitationally bound to one another, increasing distances reduce the likelihood of close encounters. As time passes, many galaxies become more isolated rather than more interactive, further limiting rapid or visible change. Older galaxies, especially elliptical galaxies and the bulges of spirals, show particularly little variation over time. These systems contain mostly old stars and little gas for new star formation. Their light output and structure remain steady for billions of years, making them appear essentially unchanged across all of recorded human history. Even changes in brightness are minimal on short timescales. While individual stars may vary slightly or explode as supernovae, these events are rare relative to the size of a galaxy. Their effects are localized and do not significantly alter the galaxy's total light when viewed from great distances. Astronomical observations confirm this stability. Photographs and measurements taken decades apart show galaxies with nearly identical shapes and distributions of light. Only with comparisons across cosmic distances, which reveal galaxies as they existed billions of years ago, do clear differences in galactic appearance become evident. In summary, galaxies appear unchanged across human history because they are governed by slow, cumulative processes. Their immense size, vast stellar populations, and long evolutionary timescales ensure continuity rather than rapid transformation. What humans observe is not a static universe, but one that changes at a pace far beyond everyday perception. The temperature conditions inside galaxies are governed by a balance between multiple physical processes that operate steadily over long periods of time. Rather than having a single uniform temperature, a galaxy contains regions with very different thermal states, each remaining relatively stable within its own range. This diversity exists without causing instability because the processes that heat and cool galactic matter tend to counteract one another gradually. Most of the volume of a galaxy is filled with very thin gas known as the interstellar medium. In many regions, this gas is extremely cold by everyday standards, with temperatures only a few tens of degrees above absolute zero. These cold regions persist because the gas is sparse and radiates heat slowly. With few particles to collide, thermal energy is not easily transferred, allowing low temperatures to remain stable for long durations. At the same time, galaxies also contain warmer regions of gas. Areas influenced by starlight, particularly ultraviolet radiation from young stars, can reach temperatures of thousands of degrees. This heating occurs gradually as radiation is absorbed by gas particles. The energy input is balanced by cooling processes, such as the emission of light at specific wavelengths, which allows excess heat to dissipate steadily rather than accumulating. Hotter gas exists in galactic halos and in regions affected by past supernova explosions. This gas can reach temperatures of millions of degrees, yet it remains extremely diffuse. Because of its low density, even very hot gas contains little total thermal energy. It cools slowly over time by emitting X-rays, maintaining a long-lasting equilibrium rather than undergoing rapid temperature swings. The coexistence of cold, warm, and hot gas within a single galaxy does not lead to conflict or rapid change. Each phase occupies different regions and follows its own thermal balance. Gravity, pressure, and radiation work together to keep these phases separated yet interconnected. Transitions between them occur gradually as gas cools, heats, or moves through the galaxy. Stars themselves maintain stable internal temperatures for most of their lifetimes. The balance between gravitational compression and energy produced by nuclear fusion keeps stellar cores at consistent temperatures for millions to billions of years. This stability ensures a steady output of energy, rather than sudden fluctuations that could disrupt surrounding environments. On a galactic scale, energy input and energy loss are closely matched. Radiation from stars provides heat, while emission from gas and dust allows that energy to escape into space. Because galaxies are large and their processes are spread out, this exchange happens smoothly. There is no mechanism for rapid, global overheating or cooling. Dust particles also play a role in regulating temperature. Dust absorbs starlight and re-emits it at longer, infrared wavelengths. This process redistributes energy rather than concentrating it, helping maintain moderate conditions within star-forming regions and across the galaxy as a whole. Over billions of years, gradual changes can occur in the overall thermal balance of a galaxy. As star formation slows, less high-energy radiation is produced, and some regions cool slightly. However, these shifts are subtle and unfold slowly, preserving long-term stability rather than causing abrupt transitions. The result of these interacting processes is a galaxy that maintains thermal equilibrium across immense spans of time. Temperature differences exist, but they are regulated by predictable physical laws. This balance allows galaxies to remain stable, enduring systems where energy flows gently and continuously, without urgency or disruption. Galaxies recycle matter through processes that operate continuously and gradually over billions of years. This recycling does not involve rapid transformations or sudden redistribution of material. Instead, it unfolds through slow cycles in which matter changes form while remaining part of the same galactic system. The overall amount of matter in a galaxy remains nearly constant, even as its internal composition evolves. Star formation is one of the central steps in this cycle. Gas within a galaxy slowly condenses under gravity, forming dense regions where stars can be born. This gas originates from material that has already passed through earlier generations of stars, as well as from gas that has remained in the interstellar medium for long periods. The process is inefficient by design, allowing only a small fraction of available gas to turn into stars at any given time. As stars age, they gradually return matter to their surroundings. Low and medium mass stars lose material through steady stellar winds during later stages of their lives. This mass loss occurs over millions of years, releasing gas enriched with elements produced inside the star. The expelled material drifts outward at moderate speeds, mixing slowly with the surrounding interstellar medium. More massive stars contribute to recycling through supernova explosions. Although these events are energetic, their role in galactic recycling is long-term rather than disruptive. The elements released by a supernova spread out over large volumes of space and take millions of years to fully mix with the surrounding gas. This gradual dispersal ensures that the galaxy's overall structure remains stable. The gas returned by stars does not immediately form new stars. Instead, it often exists in diffuse states for long periods, cooling slowly through radiation. Over time, portions of this gas may become part of molecular clouds, where conditions allow new star formation to occur. This delay introduces a natural pacing to the recycling process, preventing rapid or uncontrolled change. Dust grains are also part of this cycle. They form in the outer layers of aging stars and in supernova remnants, then drift through the galaxy embedded in gas. Dust can survive for long periods, absorbing radiation and influencing the cooling of gas. Eventually, dust may be incorporated into new stars or destroyed and reformed, continuing its participation in the galactic cycle. Galactic recycling is not perfectly closed, but losses and gains occur slowly. Some material escapes into galactic halos or intergalactic space through gentle outflows, while other material may be accreted from the surrounding environment over very long timescales. These exchanges are minor compared to the total mass of a galaxy and do not disrupt the overall balance. Over billions of years, repeated cycles of star formation and mass return gradually change the chemical makeup of a galaxy. Heavier elements become more common, while lighter elements are redistributed. This chemical evolution happens incrementally, layer by layer, without sudden shifts in composition. Throughout this process, the recycling of matter supports long-term continuity. Matter is neither rapidly consumed nor quickly exhausted. Instead, it moves through different states, maintaining a steady rhythm that allows galaxies to persist for vast spans of time. The slow circulation of material reinforces the sense of stability that characterizes galactic environments. Elements within a galaxy are distributed gradually through well-understood physical processes that operate over immense spans of time. Nearly all elements heavier than hydrogen and helium are created inside stars. Their movement through a galaxy is not sudden or concentrated, but occurs through slow release, dispersal, and mixing across billions of years. In the early universe, galaxies consisted almost entirely of hydrogen and helium. As stars formed and evolved, nuclear fusion in their cores produced heavier elements such as carbon, oxygen, silicon, and iron. These elements remained locked inside stars for most of their lifetimes. Only when stars aged did this material begin to return to the surrounding space. Low and medium mass stars release elements gently. As these stars approach the end of their lives, they shed outer layers through steady stellar winds. The expelled material moves outward at relatively modest speeds and spreads into the surrounding interstellar medium over long periods. This gradual release ensures that newly created elements do not remain concentrated in one location. more massive stars contribute through supernova explosions. While energetic, supernovae do not instantly distribute elements across a galaxy. The material ejected expands into space, forming remnants that grow over tens of thousands of years. Over millions of years, turbulence and large-scale gas motion mix these elements into wider regions of the galaxy. Once released, elements travel through the galaxy as part of gas and dust. Galactic rotation slowly carries this material along spiral arms and through disks. This movement is steady and predictable, governed by gravity and orbital motion. Over hundreds of millions of years, elements become broadly dispersed rather than clustered near their original stars. Mixing within the interstellar medium further smooths element distribution. Gas clouds collide gently, merge, and separate again. Shock waves from stellar activity propagate slowly and fade with distance. These processes blend material from different regions, reducing sharp variations in composition and creating gradual transitions instead. As new stars form, they incorporate the elements present in their local environment. Each generation of stars reflects the accumulated chemical history of the galaxy up to that point. Over time, the average abundance of heavier elements increases, but this increase is slow and continuous rather than abrupt. Different regions of a galaxy can show slight differences in composition, especially between inner and outer areas. Inner regions often contain somewhat higher concentrations of heavy elements due to longer histories of star formation. Even these differences, however, develop gradually over billions of years and remain stable on short timescales. Elements also exist in long-lived reservoirs. Some remain in diffuse gas, some are locked into dust grains, and others become part of long-lived stars. These reservoirs exchange material slowly, preventing rapid depletion or accumulation in any single phase. The calm distribution of elements contributes to the overall stability of galaxies. Chemical change proceeds incrementally, guided by predictable stellar life cycles and large-scale motion. Rather than dramatic shifts, galaxies experience a slow enrichment that unfolds quietly, reinforcing their long-term continuity across cosmic time. Galaxies do not move toward a specific destination or endpoint. Their motion is governed by gravity, the distribution of mass in the universe, and the expansion of space itself. There is no final position that a galaxy is approaching, no central location toward which all galaxies are drawn. Instead, each galaxy follows a path shaped by its local environment and the large-scale structure of the cosmos. On small scales, galaxies move within groups and clusters. These motions take the form of slow orbits around shared centers of mass. The paths are not straight lines and not directed toward completion. A single orbit within a galaxy group can take billions of years, and even then, the orbit does not represent progress toward a goal. It is simply a stable pattern of motion maintained by gravity. On larger scales, galaxies participate in the overall expansion of the universe. As space expands, galaxies that are not gravitationally bound move farther apart over time. This separation is not a journey toward a destination, but a natural consequence of space itself stretching. Each galaxy remains centered in its own local frame, while distances between distant systems increase smoothly. The large-scale distribution of galaxies forms filaments, walls, and clusters separated by vast voids. Galaxies drift slowly within this structure, guided by subtle differences in gravitational density. Over billions of years, some galaxies move toward denser regions, while others remain in lower density areas. These motions are not directed by intent or urgency, but by long-established gravitational conditions. Because gravitational forces weaken with distance, galactic motion tends to be stable rather than accelerating. Once a galaxy settles into a particular gravitational environment, its motion becomes predictable and repetitive. There is no mechanism that causes galaxies to suddenly change course or rush toward a new location under normal conditions. Even when galaxies interact or merge, the result is not a final destination. A merger produces a new, larger galaxy that continues to move within its environment, following the same physical rules as before. The process alters structure, not purpose. After the merger, motion continues without resolution or endpoint. From within a galaxy, there is no reference frame that reveals a direction of travel. Stars, gas, and planets move together through space, maintaining their relative positions. The galaxy does not experience forward motion in any meaningful internal sense. There is no sensation of approaching or leaving anything behind. Over cosmic time, the universe does not organize galactic motion toward convergence. Instead, large-scale expansion increasingly separates unbound systems. This trend reduces interactions and reinforces isolation rather than drawing galaxies together. Motion continues, but it does not lead toward a shared conclusion. The absence of a destination is a fundamental feature of galactic motion. Galaxies exist within an evolving universe where change occurs through continuous movement rather than arrival. Paths extend indefinitely, shaped by conditions that persist over immense timescales. In this context, galactic motion can be understood as ongoing rather than purposeful. Galaxies move because gravity and expansion require motion, not because they are headed somewhere. This lack of direction contributes to the calm, timeless character of the universe on its largest scales, where motion and stillness coexist without urgency or finality. Galactic motion is characterized by repetition rather than novelty. The paths followed by stars, gas, and entire galaxies repeat in stable patterns governed by gravity and conservation of energy. Once established, these motions persist for immense periods of time with only minor variation. This predictability is a fundamental property of large gravitational systems. Within a galaxy, most stars move along regular orbits around the galactic center. These orbits are not identical, but they are consistent. A star may take hundreds of millions of years to complete a single orbit, yet each orbit closely resembles the last. Over billions of years, the same paths are traced again and again, creating long-term stability in the galaxy's structure. Gas and dust follow similar repeating motions. Interstellar clouds orbit the galactic center along with stars, slowly circulating through spiral arms and disks. While local conditions within a cloud may change, the large-scale motion remains steady. The same regions of a galaxy experience similar flows of material over vast spans of time. Spiral arms themselves are examples of predictable repetition. They are not fixed collections of stars, but long-lived density patterns. Stars and gas enter and leave these regions as they orbit, while the spiral pattern persists. This creates a repeating cycle in which material passes through the same gravitational features over and over, without requiring permanent attachment. On the scale of galaxy groups and clusters, repetition also dominates. Galaxies orbit shared centers of mass along extended, looping paths. These motions repeat over billions of years, with galaxies returning to similar positions relative to one another. While small changes accumulate, the overall pattern remains recognizable across cosmic time. Even interactions between galaxies often follow predictable sequences. When two galaxies pass near each other, gravitational effects develop gradually, peak, and then diminish. If they do not merge, they continue along modified but still stable paths. These encounters do not introduce randomness but fit into broader, repeatable gravitational behavior. The expansion of the universe does not disrupt this repetition on local scales. Within gravitationally bound systems, expansion is negligible, allowing orbital motion to remain consistent. On larger scales, the increase in distance between unbound galaxies proceeds smoothly, following the same rate of expansion everywhere. This uniformity reinforces predictability rather than chaos. Physical laws ensure that galactic motion does not drift arbitrarily. Conservation of angular momentum, energy, and momentum constrain how systems can change. As a result, motion settles into long-lasting patterns instead of evolving unpredictably. Once established, these patterns are resistant to rapid alteration. Because repetition dominates, galaxies exhibit continuity rather than constant transformation. Motion is ongoing, but it revisits familiar states. Positions shift, yet the underlying structure remains intact. This repeated movement creates the impression of stillness when observed over short timescales. The predictable repetition of galactic motion reflects a universe governed by stable rules. Large systems follow paths that endure, cycle, and recur. Change exists, but it unfolds within repeating frameworks that preserve order across billions of years, allowing galaxies to persist as calm, long-lived structures within an immense and steady cosmos. Galaxies remain stable despite constant internal movement, because the motions within them are balanced and governed by long-standing physical laws. Every galaxy contains billions or trillions of individual components, stars, gas clouds, dust, and dark matter, all moving simultaneously. Stability does not arise from stillness, but from the way these many motions are organized and regulated by gravity. Stars within a galaxy travel at high speeds, often hundreds of kilometers per second, yet their orbits are shaped by the combined gravitational pull of the entire system. This shared gravitational field prevents stars from flying outward or collapsing inward. Instead, stars settle into long-lasting orbital patterns that distribute motion evenly across the galaxy. Each star's movement contributes to the overall balance rather than disrupting it. Gas within galaxies is also in constant motion. It drifts, rotates, and circulates through disks and spiral arms. While gas can compress locally to form stars, most of it remains diffuse and moves gradually. Pressure, gravity, magnetic fields, and radiation interact to prevent rapid collapse on large scales. These forces counterbalance one another, allowing motion without instability. Dark matter plays a crucial stabilizing role. Its extended halo surrounds the visible galaxy and provides additional gravitational support. This halo smooths out variations in motion, ensuring that stars and gas remain bound even at large distances from the galactic center. Without this unseen mass, many galaxies would not be able to maintain their structure while in motion. Galactic disks are stabilized by rotation. As a galaxy rotates, centrifugal effects balance inward gravitational pull. This balance prevents large-scale collapse while allowing material to continue moving along circular or gently elliptical paths. Over billions of years, rotation helps preserve disk shapes even as individual stars complete many orbits. Internal disturbances do occur, but their effects are usually localized and temporary. Star formation, stellar winds, and supernovae inject energy into the surrounding gas. However, this energy disperses over large volumes and long timescales. The galaxy absorbs these disturbances without global disruption, returning to equilibrium through gradual cooling and redistribution of material. Gravitational interactions between stars are generally weak because of the vast distances separating them. Direct stellar collisions are extremely rare. Instead, stars influence one another collectively through the smooth gravitational field of the galaxy. This reduces chaotic behavior and supports long-term stability. Even structural features such as bars and spiral arms do not destabilize galaxies. These features arise naturally from internal motion and redistribute energy and angular momentum slowly. They evolve over long periods without causing the galaxy to lose coherence. Their presence reflects regulated motion rather than disorder. The laws of conservation play a key role in maintaining stability. Angular momentum and energy cannot change abruptly in large systems. As a result, motion within galaxies adjusts gradually, preventing sudden or catastrophic reorganization. Large-scale balance is preserved even as small-scale changes occur. Because of these regulating factors, galaxies demonstrate that continuous motion does not imply instability. Movement is constant, but it is organized, constrained, and predictable. The galaxy persists as a coherent system, where countless motions coexist without conflict, maintaining structure and continuity across billions of years. Stars, gas, and dust coexist within galaxies in a state of long-term balance that emerges naturally from their physical properties and shared gravitational environment. Each component behaves differently, yet their interactions are regulated in ways that promote stability rather than disruption. This harmony is not static, but it persists through continuous adjustment over immense spans of time. Stars make up most of the visible mass of a galaxy and follow predictable orbital paths around the galactic center. Their motion creates a stable gravitational framework within which other material moves. Because stars are widely spaced, direct interactions between them are extremely rare. Instead, they influence their surroundings collectively, contributing to a smooth and persistent gravitational field. Gas exists in multiple forms within a galaxy, from cold molecular clouds to warmer diffuse regions. It moves under the influence of gravity, pressure, radiation, and magnetic fields. While gas is more responsive to local forces than stars, its motion remains gradual on large scales. Gas clouds drift, compress, and disperse slowly, adjusting to the overall structure of the galaxy rather than overwhelming it. Dust consists of tiny solid particles mixed throughout the interstellar medium. Although dust makes up only a small fraction of a galaxy's mass, it plays an important role in regulating energy. Dust absorbs starlight and re-emits it at longer wavelengths, redistributing energy without concentrating it. This process contributes to thermal balance and supports steady conditions in regions where stars form. The interactions between stars, gas, and dust are continuous but gentle. Gas and dust respond to radiation and gravity from stars, while stars are largely unaffected by the detailed motion of gas and dust around them. This asymmetry prevents feedback loops that could destabilize the system. Each component influences the others without dominating them. Star formation is a key point of interaction. Gas and dust gradually condense to form new stars, but this process is inefficient and slow. Only a small fraction of available material becomes stars at any given time. This limitation prevents rapid depletion of gas and allows the galaxy to sustain star formation over billions of years without dramatic shifts. Energy input from stars, such as radiation and stellar winds, affects gas and dust locally. These effects can heat or disperse nearby material, but they fade with distance and time. The galaxy absorbs this energy and redistributes it, maintaining overall equilibrium. Local change does not translate into global instability. On large scales, the combined motion of stars, gas, and dust aligns with the rotation of the galaxy. All three components participate in the same general orbital flow around the galactic center. This shared motion reduces friction and conflict between components, reinforcing coherence across the system. Over long periods, matter cycles between these components. Gas and dust form stars. Stars return material to the interstellar medium, and that material mixes back into gas and dust. This cycle proceeds slowly, ensuring continuity rather than abrupt transformation. The proportions of stars, gas, and dust change gradually, preserving balance at each stage. The quiet harmony between stars, gas, and dust reflects the broader nature of galaxies as regulated systems. Multiple forms of matter move together under common physical laws, adjusting continuously without urgency. The result is a stable environment where complexity exists without chaos, sustained across billions of years by predictable, well-balanced interaction.